from the previous stuff. So you guys should have worked on worksheets 1 and 2 here a little bit. We'll start with questions from those, and then we'll kind of move on a little bit and call it a day. Sound good? Amanda. Sure. Worksheet 2, number 11. So I'm going to start by figuring out what two quadrants theta can lie in by figuring out where 3 pi to 4 pi is. So 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and then 4 pi. So 3 pi to 4 pi is quadrants 3 and 4. Of those two quadrants, using all silly turtles crawl, cosine is positive in quadrant 4. So I have once around, and then there is my theta. So far, so good? Okay. My alpha is formed by the x-axis and the terminal side. So far, so good? Where alpha is going to be cosine inverse of the absolute value, 0.87. And since the last axis we crossed here, or since theta is positive, and the last axis we crossed is vertical, I know we're going to have 4 pi minus alpha. And then it's calculator time. Is this okay so far, Amanda? Okay. So that's 12.05. And just to check things, cosine of 1205 should be 0.87, which it is. And 1205 should be bigger than 3 pi, which it is. And still less than 4 pi, which it also is. So that looks like my answer. Does that feel okay there?
Yeah, I did.
I'm sorry, you mumbled a little bit. Oh.
The answer key is different.
Oh, my apologies.
It also says to do like subtract 2 pi from each side, so like the 3 pi and then 4 pi, maybe like between pi and 2 pi. Can we do that?
I mean, if you want, it's the same thing as what I'm doing here.
And I have a question.
Because when you do that subtraction, you end up adding it back on at the end. So like, if you want to just go around one time instead of, it's all the same. You know what I mean? Tommy?
Can you do number 11 on worksheet?
Sure. Okay. So same idea. I'm going to cut to the chase because this is also 3 pi to 4 pi, so we already know that it's down there, right? And then all silly turtles crawl. So tangent is positive in quadrant 3. So that's my theta, right? Okay. So this one I'm going to the unit circle. So I remember tangent is y over x. And the problem here is that y should have a square root of 3 in it. And the x-coordinate should have a regular 3 in it, but there's nothing on the unit circle who has a regular 3 in it, right? So what we'll do here instead is we're going to reduce this. So I know regular 3 is square root of 3 over, or times square root 3. So that reduces down to 1 over square root 3. So I'm going to look in this unit circle for where the x-coordinate has a, or the y-coordinate has a 1 in it, and the x-coordinate has a square root of 3 in it. And that is something that'll work. Let me grab this and drop that in. So if I go to quadrant 3, where the y-coordinate has a 1 in it, and the x-coordinate has a square root 3 in it, is 7 pi over 6. But that is too small. Doesn't fit in my interval. So I know I'm going to be adding 2 pi to it one time, because when I draw the picture, I'm going around one time more. And when I do that, I get 19 pi over 6, which is my answer that I'm looking for. Is that okay, Tommy?
Yeah.
Apologize for my voice. It feels like I'm going through puberty again with my voice keeps doing this. Jake. 7 from worksheet 1. Okie dokie. Oh, I didn't take both pages, but I got to what I needed. Okay. So I have cosecant here. The first thing I want to do is rewrite this so that it's in terms of sine, cosine, or tangent. I remember that cosecant is the reciprocal of sine. So I can just replace cosecant with 1 over sine. And then if I flip both sides, that's the same thing as sine equals, or sine theta equals 1/2. Draw my picture, so 0, pi over 2, pi, 3 pi over 2. So we're looking at quadrants 2 and 3. Of those quadrants 2 and 3, sine is positive, only in quadrant 2. So that's what I'm looking for. So I'll go to my unit circle, look in quadrant 2 for a spot where the y-coordinate is 1/2. And I see that right here. My answer is 5 pi over 6. Cool? What do you guys think? Doing okay on this? Takes a minute to get the hang of it, but once you get the hang of it, they're like all really the same, which is nice, right? You know, there's no like goofy way you have to do something. They're all just kind of the same. Cool. Okay. If you guys change your mind, we can always come back and do more later, right? They don't ever go off the table here. So there's 2 more ideas here in 4.1 that I want to continue talking about, and then we'll deal with 4.2, which is pretty short. So one thing I forgot to mention in 4.1 is notation related. So in 4.1 we defined sine inverse, cosine inverse, and tangent inverse, right? There's kind of an equivalent way of writing these things, an equivalent notation that for our purposes means the same thing. So sine inverse, also the same thing as arc sine. Cosine inverse, same thing as arc cosine. And tangent inverse, the same thing as arctan. So that's just like a notation thing. Those two symbols can be used kind of interchangeably. It's been a long time since I remember talking about the derivation of arctan or arcsine. I can't remember if it's the exact same derivation as the inverses, but for our purposes, they can be used interchangeably. Okay. So that leads me to this question. So let's say that we have arctan of tangent 5 pi over 4. And we just want to evaluate this. What is this thing going to equal? I think it's just 5 pi over 4. What do you guys think? No, unfortunately. So these two things are acting as inverses, right? So what's the holdup? Remember the range for tan inverse or arctan is negative pi over 2 to positive pi over 2. Is 5 pi over 4 in that interval? No. So can it be output from arctan? No. Okay, so what should I do? Well, here's what we do. We're going to have to do this the long way. So we're going to go ahead and work from the inside out. So I'm going to calculate tangent of 5 pi over 4. So y over x gives me 1. Everybody cool with that? Tangent of 5 pi over 4 is just y over x. So that's just 1. So we have arctan of 1. So remember, arctan is going to give me something in quadrants 1 or 2. Or I'm sorry, 1 or 4. Of quadrants 1 and 4, tangent is positive, only in quadrant 1. So I'm looking for the place in quadrant 1 where y over x gives me 1. That happens at pi over 4. And there's my answer. Is that okay? If it's not, speak up and I can say it again or rehash it or fill in some more detail or whatever. It's okay if you didn't understand the first time. Again, it's your first time doing it, so it's no big deal. But the gist of it, the big takeaway here is when you have an expression like this, you have to be a little bit careful about these inverses and trig functions don't necessarily just kind of cancel all willy-nilly if you have a specific number value inside of there. If it's a variable, you can cancel things willy-nilly. It's not a big deal. But if it's it's an actual number there, you might be trying to say that, this inverse is outputting something that's impossible. You know what I mean? Everybody okay with that idea, though? Not too difficult. But if you hadn't seen it before, you would not probably think that, right? That's something that once it's pointed out to you, like, oh, yeah, okay. But without having seen it once before, it's maybe a little bit sneaky there. All right, one more example of something. So let's say we want to find an algebraic expression for sine of arc cosine of 2x. So here's the idea. We're going to work again from the inside out. So remember, if I do a cosine inverse or an arc cosine like this, what I'm getting back is an angle measure. Everybody's okay with that? And this theta equals arc cosine of 2x is equivalent to just saying cosine theta is equal to 2x, right? Welcome back, Chinese field trippers.
Hi.
How are you?
Incredible.
Okay.
Yeah.
Are you Inspector Gadget?
No, my name is Borat. I'm Borat
Oh,
from
from
Borat.
that's good.
And I'm missing the mustache because I don't have tape to put it on.
Oh, that's a shame.
It really is.
Okay. Everybody still good with cosine theta equals 2x? What I'm going to do now is I'm going to think back to my right triangle definition for cosine. So 2x is really adjacent over hypotenuse. So I'm going to draw a right triangle. I'm going to designate one of the acute angles as theta. And then I'm going to write 2x as the adjacent side and 1 as the hypotenuse. Everybody's okay with that? So if I want to do then sine of theta, I'm going to go look at my triangle that I have and go back to my right triangle definition for sine, which is opposite over hypotenuse. But I don't have the opposite side of this triangle. How could I find it? Sydney? Pythagorean theorem sounds great. I'm going to call that side A for the time being. So I have a squared plus 2x squared equals 1 squared. 2x squared is 2x times 2x, which is 4x squared. 1 squared is just 1. I'll subtract 4x squared from both sides. And then I'll square root both sides. Notice when I square rooted both sides, I dropped the plus or minus and just chose this to be positive. Why am I allowed to do that? It's a side length for a triangle, right? Side length's gotta be positive. Sydney? Of course. Quick question. So square root of 1 minus 4x squared, that's just 1 minus 2x, right?
Wow.
No.
How could we ever? No.
I've caught many people doing this year. Remember, radicals, you can't break a radical across an addition or subtraction symbol. You can break radicals at multiplication and division, but not at addition and subtraction. So that can't be simplified any further. So sine theta then is just opposite over hypotenuse, or just 1 minus 4x squared. So that's my algebraic expression. Amanda, you're making some faces. What's going on? Oh my goodness, I didn't mean to. Thank you. If it feels like I'm making a mistake, please speak up. You don't have to it's very possible I just goofed something up. If I did and then it was still okay and you were wrong, no big deal. I'm not gonna be like, why'd you interrupt me when I was right? It's just gonna be like, oh, let's just double check. Okay, nope, that still looks good. No big deal. But if you think I made a mistake, please say something. Sooner the better, so we don't have to change a lot. This was okay because it's right at the end, so I didn't have to redo a whole bunch of calculations. Paul, what's up? Same thing as the inverse. That's it. Yeah, that's all it's saying.
Why do you write it down?
It just, they're often two different notations developed because two different groups of mathematicians were doing the same thing at the same time using different notations because they was 300 years ago when communication was really slow.
Uh-huh.
Or there was no way to communicate between them because maybe it's like somebody's doing this in like Eastern Europe and somebody's doing it in America.
That could be a pretty good reason, I guess.
You know, so there's a lot of notation in mathematics where you have like multiple ways to write the same thing because different groups of people were doing it using different notation, weren't really communicating a whole lot because there wasn't a lot of journals being published 300 years ago.
Are there different forms of sign then?
I think we all write it as sign. I haven't seen anything different than that, but part of it's just like a history thing, you know, like when you talk about when you do calculus next year, you'll see there's like a bunch of different notations to do some of these operations on calculus because you had two people developing the tools of calculus kind of at the same time independently of each other with completely different notations. So it's fun. Nobody wants to agree to just like, hey, let's all just use this because people are like, no. In my specific field, this makes it so much cleaner if I write it this way. So nobody's willing to give up on any of it. So we're just stuck with like lots of ways to write some of these things.
Fun.
Yeah. Go ahead. Okay. That was the last of the stuff in 4.1 that I hadn't gotten to show you. I didn't show you yesterday, mostly because I just wanted to focus on that singular skill from last time that I didn't want to bog down with a bunch of other stuff, but we needed to make mention of that because that stuff is going to come up. We'll do 4.2 now. This is a pretty light section. So we have just 2 pieces of vocabulary and then some example problems, and we're in and out on 4.2. You guys good with that idea? I think that's a good plan for a Friday that's Halloween. So I'm going to define 2 things here, but I'm going to just use a picture to define them, because that's how we're going to be using these 2 terms, is just drawing pictures with them. So I see no reason not to just define it with a picture. So these 2 terms are angle of elevation and angle of depression. Suppose you have 2 people, one person standing on the ground, one person standing at some elevated position. Okay, the person on the ground, let's say they naturally are just heading in a neutral position with their eyes forward. And then they raise their head up a little bit to look at the person up on the elevated position there. We call this our angle of elevation. I'm just going to abbreviate that AOE. Everybody cool with that? Similarly, the person at altitude, their line of sight is just kind of at the head neutral position. If they look down to look at the person on the ground, this angle formed is called your angle of depression. What do you notice about these 2 angles geometrically? They're congruent. Why?
Because there was a property in geometry a while ago.
Yeah. Does anybody remember the name of that? Very good, Robbie. Robbie says alternate interior angles.
Yeah, Robbie.
So this works because those lines of sight are parallel. And we know that if parallel lines cut by a transversal, the alternate interior angles are congruent. Again, not important that you remember the names of those things, but rather just that, like, yeah, okay, those 2 angles are going to be the same. That's good enough. But since it's math class, and I remember, I'm going to remind you. No one will expect you to remember the names, but if you do, you can impress some people. And I'm all about impressing people. You know what I mean? Why study all this mathematics if you can't impress anybody with it? You know?
That's all I know.
That's the only reason I'm getting this stupid PhD, is just to impress people. All right. So let's just do a couple of examples. The problems in this section are all going to be word problems. So we're going to be using this angle of elevation, angle of depression specifically to kind of draw the pictures involved for these word problems. So this one reads, Christy is looking up at the Fisher Building in downtown Detroit. She's standing 200 feet from the base of the building and finds the angle of elevation to the top of the spire to be 66 degrees. How tall is the Fisher Building? So I'm going to just draw this picture as if it's a triangle. So there's Christy, there's the top of the spire. It says it's 200 feet away, and the angle of elevation is 66, so that's that angle there. And we're interested in how tall this building is. So that'll be my X. Everybody cool with that? How am I going to solve for X here?
Finding.
Yeah, since it's a right triangle, I can just use SOHCAHTOA. So this is adjacent and opposite. I should be using tangent. So tan 66 is opposite over adjacent. Multiply both sides by 200. I have 200 times tan 66 should give me X. Before I type that into my calculator, I need to make sure I'm in what mode? Degree. Notice the angle here has a degree symbol on it. Probably everybody was still in radian mode from the last time we worked on the homework.
Yes, I'm going to review it because I got very confused when I looked at my work and the answers. I was like, oh.
So 449 feet. What noodle place did you go to?
Noodletopia.
Where's that at? Madison Heights has all the noodle places.
The Chinese, they're mini Chinese yogurts and they're delicious.
Okay. All right. Another example.
They're chili.
Everybody's good with the first one, though? Okay. Here it says Jane has climbed a tree and is looking down at her friend Mary. So we'll draw this as a picture. So J, I'm assuming the tree is growing at a 90-degree angle, perpendicular to the ground. It's a fair assumption. Just like we assumed the Fisher Building was perpendicular to the ground. Well, then would be a more difficult problem. Okay. Jane has climbed 17 feet into the air, and the angle of depression to Mary is 49 degrees. Now, here's the tricky part. Where's the angle of depression really at? That's your angle of depression, right? So this is also 49. And then how far is Mary standing from the base of the tree? X. How are we going to solve for X? Yeah. Tan 49 is equal to 17 over X. Multiply both sides by X. And then divide by tan 49. And then it's calculator time. Calculator time. 1478. So far, so good. Everything pretty straightforward so far, right? This is the most difficult version of the examples. So here we have Claude and Simone are riding bicycles in Paris. At one point, they stop and look up and measure the angle of elevation to the top of the Eiffel Tower to be 32 degrees. When they pedal 100 meters closer to the tower, the angle of elevation changes to 37.5 degrees. How tall do they estimate the Eiffel Tower to be? So the trick here is that we don't know both or two sides of the right triangles here. There's really two right triangles present, right? So what we're going to do, I'm going to label this side length as y, and we're going to end up solving a system of two equations. So I'm going to draw two right triangles. Let's use a red to indicate what we're doing here. So if this side is 32, that side is x. What is the adjacent side here got to be? 100 plus y, right? If I draw my other right triangle, 37.5 degrees, that side is x. What's the adjacent side for this one? Just y. Very good. So from the first triangle, I can write that tan 32 is equal to x over 100 plus y. And from the other one, I can say tan 37.5 is equal to x over y. That's going to form a system of two equations. I think the easiest way to solve this is going to be to get the x's by themselves and then set the two equations equal to each other, solve for y, and then plug back in to find x. X is really what we're looking for. So like computationally, I'd rather solve for x, like substitute y out and solve for x directly. But I think that algebraically, that's going to be kind of a pain in the tuchus. So I'm going to just solve for y and then compute x afterwards, because I'm looking at the algebra involved and it looks a lot easier. So for the first equation, I'm just going to multiply both sides by 100 plus y. That gets x by itself. And I multiply the other equation by y. That gets x by itself. This is why substituting for x is going to be easier, because I don't have any fractions anymore. Since both of these two equations are equal to x, I can just set them equal to each other. So far, so good. We'll distribute through that tan 32. To get y by itself, I got to get all the y's on one side. So I'm going to just subtract y times tangent 32 from both sides. Oops. And I can factor a y out of that to get the y in just one place. And then divide both sides by tan 37.5 minus tan 32. So on my calculator, I'm going to use the fraction command. So I'm going to do alpha y equals, and then choose the numerator over denominator. Just because it was going to be a lot of parentheses to get that to do what I wanted to without using the fraction command. But by using the fraction command, I can just type it in the way it looks on my paper, and that feels way simpler. And my life is hard enough. If I can make my life a little bit easier, I'm excited for that. So y is about 438.6. But that's not what I want. We wanted to solve for x. So I'm just going to use this equation here to solve for x. So I know that x equals my y times tan 37.5. So we'll go back to my calculator, do ands times tangent 37.5. So 336.6 is about my height. Everybody okay with that? Again, like, the setup is probably the worst part. Once you realize that you have to solve the system's not so bad. This feels like a good place to stop. What do you guys think? Okay. For the problem set on Sunday, it's just going to be worksheets 1 and 2. You should be able to do for next week's problem set on the 7th. We're going to start with 1 through 18 and worksheet 3. And we'll add to that as the week goes on. We still have to let first and second hours catch up, so we'll have next week will be a little bit of a slower pace for you guys in 5 and 8. Since I was gone that day and they didn't do as much as you guys did on the day when I was here, so it's okay.